identify the 4 compartments. There are 4 compartments here. Okay, you can still identify the 4 sections here. Okay, let's start with the circuit breaker. Where is it? You can zoom in, class, you can zoom in yourself. Okay, now make it big, bigger, but now it's a little bit too small. Now, by the way, you can also watch videos, from the internet. A lot of videos from switchgear company like ABB, GE, Siemens, and also, like Mitsubishi, or these high voltage company, they make switching devices. Okay, now look here. Where's the switch? No, the circuit breaker first. Okay. Let me use the red one. Can you tell the circuit breaker here? Some say, yeah, I can see it. That's correct. This part is the circuit breaker, isn't it? Yeah, that's the circuit breaker. Okay, squared the circuit breaker. Then where's the bus bar? Usually it's on top of the circuit breaker. This one is the bus bar. Can you see the three bus bars over there? Okay, then you go below, you can see the bottom part of this picture, right? You can see the cables. Now these are the cables. Now where's the VT, voltage transformer? That's the one. Now this is a VT. Okay, now what is this? CT, remember, current transformer, right? Okay, so you have let me use a different color. Now this one, and now together this one, and one more, right? Circuit breaker, bus bar, the cable compartment, and also one more, remember, for instrumentation for CTs. See here, that's the one. So roughly, all the high voltage switchgear assembly, consists of 4 parts. Maybe the design, can vary, but generally speaking, right, you have these different parts. Okay. So with this, right, you can have a better understanding of that. Now this some zoomed in view, right, of each part. You see the bus bar is here, cables here, right? Current transformer, voltage transformer. There's an earth bar. Now, earth bar is also important here. So the earth bar, yeah, is this part. Yeah, sometimes, yeah. So the okay. So that's the, now this one is the circuit earth switch. You see, when you take out the circuit breaker, you see now these are the connecting point for circuit breaker. Now circuit breaker has shutters. That means, okay, now we go back to the previous one. Mechanical device, to protect the assembly. So you see the shutters here, shutters. You see this one is the shutters. That means when you withdraw your circuit breaker, you take out the circuit breaker, these shutters will close automatically, slide down actually, to close the fixed connecting points. Because you take out your circuit breaker, this part is still here, remember? This part doesn't go with the circuit breaker, right? Okay, so that's the safety feature. One is the safety shutters. Then earthing switch. Now there is an earthing switch, right? Earthing switch basically is to earth the cables or to earth the bus bar, depends on the requirement, right? Now that's the first function. Now secondly, the earth switch, right, also needed to discharge the cable, because the cable, the charges can be stored in the cable. So you have to discharge it before you can do anything. For example, service to your cable. Now, this is important. How to discharge the stored charges? Then you have to use the earthing switch. Okay. The other one is the safety interlocks. Now, safety interlocks, this one is different from the bus coupler. Remember, I write down here. Remember the bus coupler. Now also has the safety interlocks, right? Remember the 3 circuit breakers cannot be on at the same time. But this safety interlock is different. This safety interlocks is for the circuit breaker only. It's for the CB only, for circuit breaker only. What is the function? Basically, it says it goes like this. Now, the circuit breaker cannot be withdrawn or inserted when the circuit breaker is in on condition. That means the circuit breaker is closed. That you cannot take it out. Yeah. So, okay, that's the one of the safety interlocks. Then the circuit breaker cannot be inserted when the earthing switch is on. That means now when the earthing switch is on, so the circuit breaker cannot be inserted back. Okay. Now basically, I removed this one. Now this one is not here anymore. So the circuit breaker cannot be inserted back to the to the position. Now, basically, basically to avoid accidental short circuit, because you sometimes engineers, electricians have been working all day long, right? So possibly they forget to remove the earth, the earthing switch. So in that case, if you push the circuit breaker back into the assembly, what will happen? Short circuit, disastrous. Okay, so that's why you have some safety interlocks for circuit breakers. Again, safety interlocks for circuit breakers is different from the bus coupler interlock. Over there, basically, is the check. The three. Over there are 3 circuit breakers involved, but here there is only 1, right? Yeah. So these are the safety features. Okay. Okay, class. Any questions you want to ask me so far? Any questions? Questions? Not yet. Not yet. Okay, thank you. Not yet. Okay, next. Now this one. Now this again, I make it a little bit, zoom in a little bit. Now this one is a typical high voltage switchboard layout. Sometimes you have many switch gears put together. So this one, for example, this is one switch gear, 2. This one is for outgoing. This is incoming. Okay, this is incoming. Incoming meaning power source. This is also incoming. Now this is outgoing, and it's the outgoing. Okay, so in between, you have the switch gears 1, 2, and also switch gear 3. But this one here is the bus bar. Now here's the bus bar, but there's a circuit breaker here. Now this one, remember, we call this bus coupler, right? Yeah. So the bus bar also here. So there must be a link, then to here. Okay. So in this case, there are 2 sets of switch gears. And this one, right? Incoming, outgoing, yeah. It can be the same design, right? It can be the same design. Okay. Then there is the incoming one. Incoming. This is also incoming, right? But we don't in the diagram, right? We don't have the details, but the details inside a switch gear actually has been discussed just in the previous slide. Remember, you have 4 compartments, right? So that's the layout. But if next week, right? If you do, maybe next time you go to the high voltage center when you do the PDP practical, you can take a look. You ask your lecturer, where's the switchboard layout? Can I take a look? Basically, you walk into the room, right? The first row, you see the switch gears. Not the first row. Then further, second row, then you see a row of switch gears. Basically, that's the switchboard. Yeah, you can see that one. I remember that one is from ABB. You can take a look. Okay, behind that switchboard is the low voltage switchboard. Yeah, it's a low voltage, 400 volts. All right. Okay. Again, here now has basically I would say it's repeating the discussion about the bus coupler, right? Remember when we talk about bus coupler, 3 circuit breakers involved, 2 incoming plus the bus coupler, right? Remember the logic, right? In topic 1, we talk about the logic. So the 3 bus couplers cannot be in the on position at the same time, right? Basically, the bus coupler is to serve as a kind of backup service. For example, backup power supply. For example, if something goes wrong here, so this circuit breaker will trip, right? So you can restore the supply from here by closing the bus coupler. Basically, it's to improve the reliability, right? And this design is also cheaper compared with the ring design, right? Because where in the ring design, the required now switching capacity is higher because of the larger fault current, the larger fault level. Okay, so anyway, you know this already, right? You learned this in topic 1. Okay. Now, just now, those few slides, now they are all about high voltage switchboard, HV, now high voltage switchboard. Next, we will take a look and spend a little bit longer on the low voltage switchboard, okay? Now, when you design a low voltage switchboard, you have to answer 4 questions. What is the operating voltage? Now, this is easy, 400 volts, yeah, low voltage one. Then what is the rated insulation voltage? Meaning the withstand voltage, because sometimes, you know, you may have, the switchboard may experience over voltage. So there should be a insulation level there. That means, okay, for this 600 volts, right? That means so long the voltage is less than 600 volts, it's safe, right? Okay, so that's the rated insulation voltage. And also the frequency, what is the frequency? And one more parameter for a low voltage switchboard is the rated short time current. Now, this one is very similar to the definition of a short time current for circuit breaker. You still remember in the previous topic. Well, what does this mean actually? What does a rated short time current? Okay, now this depends on the prospective fault current at the switchboard. Okay, usually rated at 3 seconds. That means, remember, when there is a fault, the fault cannot be cleared, um, you know, immediately. There should be there will be some delay because circuit breaker is a mechanical device. Now you have to allow some time for the mechanical device to disconnect the circuit, disconnect the fault. Okay, so during this period, before the circuit breaker trips the fault, the switchboard will see the short circuit current, right? Yeah, the fault current will go through the switchboard. So during these first 3 seconds, the switchboard cannot fail. Okay, that means you cannot see fire. Okay, that's a problem, right? That means the design is a failure. Okay, so that means the switchboard can take the fault current for 3 seconds. That's the design requirement. Okay, so after 3 seconds, the switchboard can fail. Now, actually, because the spec doesn't say, you know, the fault current will go through the switchboard for more than 3 seconds, right? So that's the meaning of rated short time current. I think some of you still remember the similar short time current for circuit breaker, the same thing. Okay, so that's the low voltage switchboard parameters. Okay, now here's one actually is a fault calculation. I believe all of you know how to do it already, but anyway, I still now just quickly go through this question. A consumer electrical distribution system receives its 22 kV supply from a power company, and a 2 MVA, 22 kV, 400 volt transformer is used to connect the supply to the consumer's 400 volt main switchboard. Okay, so from this description, you can draw a diagram actually. Now it goes like this. Now you see incoming 22 kV, then there's a step down transformer, then to the main switchboard. This one is the 400 volts switchboard. Okay, 400 volts. So this side is 22 kV. The other side is, of course, 400 volts. Okay, so the incoming is here. Now this is the incoming. Okay, this is the incoming. Now, if the percentage impedance of the transformer is 5%, that's the parameter you need later on. What is the maximum perspective of fault level at the 400 volt switchboard? That means how much is the short time current the switchboard has to withstand. Okay. Okay, now it's here. Now there are more. Now these are the feeders, right? These are the feeders to your consumers. Okay, so the question basically says, now if there is a fault somewhere here, okay, fault is here. So how much is the fault current? Okay, from the calculation viewpoint, right, it's pretty easy because fault MVA is equal to remember the SB divided by ZPU. Now SB is the transformer capacity. ZPU 5%. You just do this. Now you got it 440 MVA. Then find the current at the switchboard side. That means divided by square root of 400 volts. Now here you go. That's the fault current. Okay. Now from your calculation, you can see yes, the short time current reading of the main switchboard of the 400 volts is 57.7 kilo amps for how long? 3 seconds. Yeah. If your design, meet this requirement, that means if there's a fault, right, it's safe because the assumption is this: after 3 seconds, the circuit breakers, will trip the fault. Okay. All right, so that's the calculation. Again, I know all of you know how to do the calculation, how to calculate this kind of fault current, right? So any questions about this one? Maybe you don't have. Yeah, just check. Anyone has a question about this one? Don't have yet. Okay. Next is about how to test a switchboard. So you design a switchboard, you make a switchboard, then now hopefully you want to sell the switchboard to a user, which may be a factory, right? So you cannot, design the circuit breaker, make the circuit breaker without doing any testing, right? You have to test the the switchboard, make sure everything is in order. Then you can, they can bring the switchboard to the factory, to the site. Okay. Then what are the tests before you deliver the switchboard you have to carry out? So the first one is the type test. Okay, I circle this type test. Then the routine test. The final one is the commissioning test. Right? That means that after the commissioning test, now the switchboard can be used. Used to supply the customers already. Okay, so what is the meaning of a type test? Okay, write down here, type test. Okay, type test basically is done by approved independent testing authority, can be a laboratory. Okay, so that means you cannot do this at your at a manufacturer's factory. So the type test must be done by an approved independent third party. Okay, usually certified, for example, by some authority or organization, right? So that's the type test. Okay, later on we have more on the type test details. Now the other one is the routine test. Now this routine test is carried out in the manufacturer's factory. That means, for example, this factory now specialize in making switchboard. So this routine test can be done in the factory. Now, the commissioning test, perhaps you have guessed it out. Now, this one should be carried out on site. That means in the plant, right? The one who is going to use your switchboard. Okay, so that's the different test. Now we take a look at the details of each test. Okay, type test. Now, why do we do the type test? Basically, to simulate different kinds of severe stress normally encountered in the real power system. Okay, severe stresses. That means rare events, but you will see it. You know, the switchboard may experience it. Okay, so more specifically, these type tests, including mechanical operation, make sure the operations is correct, and temperature rise, high voltage power frequency test, and also a partial discharge and the BIL. BIL stands for basic impulse insulation level. That means you apply kind of impulse to test your device. Sometimes this kind of test can be destructive. That means if your device cannot survive this kind of test, then you have to redesign or redo your switchboard. Short circuit test, terminal test. That means really short circuit the terminal, short circuit the terminals, and test the switchboard, including internal arc faults. Okay. Then also environment test, especially for example, if your switchboard going to be used in for example marine industry, then so the environment is very different, right? Because the environment over there is harsher. Yeah, and also the EMC, electromagnetic compatibility test. That means does this the switchboard affect other control or communication devices? Okay, so this is another test. Remember, type test is not by the manufacturer of the switchboard, is done by a third party, certified company, right? Sometimes the laboratory may be overseas, so you can tell this kind of type test is costly because you have to ship your switchboard finished product then to the factory, to the laboratory. All right, so this is the type tests. Now, routine tests are a little bit simpler. Routine tests basically the purpose of which is to to carry out in the factory just to confirm every production unit is identical to the unit that has gone through the type test. Okay, so you understand the meaning of the routine test, meaning something like you have a prototype, that one has gone through all the type test. Now you want to make more. You pass the test. Now it's something like a mass production. You want to produce more, so you have to do routine test. Now the routine test includes visual inspection, check all the parts whether it's okay or not. Yeah, sometimes the experienced engineers, technicians, can see the problem. They know, they have the knowledge, they check, they just do a visual check, they know whether the parts are correct or not. Then dielectric insulation test, also called voltage withstand test, on the main circuit control and the auxiliary circuit. And also checking the electrical continuity. You have some parts joined together, right? So the resistance should be very small. Yeah, you can use some meters to check this. And also the protection circuits continuity. Also measuring the resistance of main circuit, how much is the resistance, cannot be too big, because you have some resistance in the main circuit. Now there will be a heating problem. That point will be overheated. Eventually, it fails. Okay, so electrical operation test for the basically for the control and protection circuits. and also mechanical operating test. Operate the devices, whether it works or not. Okay, so these are the routine tests, right? Now it's done in the factory. Okay. Okay, any questions so far? So see, we finished the test, the type test and the routine test. Now it's time to conduct commissioning test. Meaning after the commissioning test, if the switchboard you design can pass the commissioning test, the meaning is ready to deliver it to the the site plant, right? Yeah. So in the commissioning test, uh, for high voltage switchboards, normally carried out before turning on the supply. Meaning, if you are doing a high voltage switchboard, the commissioning test is done before the switchboard is energized. Okay, before you turn on the power supply. Then for the low voltage switchboard, now you have to do both. Some tests are before the switch on, not turning on. Some of the tests are after the supply is switched on. So there are two parts. Now the test before and after the supply is turned on. Okay. Then what are the commissioning tests now you have to do as a switchboard manufacturer? Now there's a long list you have to carry out. So there are many items on the list. Now you have to do a primary current injection test. Now this is a large current injected in the primary side, so that you can test the current transformer over current relay and earth fault relay. So this primary current injection test can check the whole circuit actually, including CT, overcurrent relay, and the earth fault relay. Okay. Then the other test is the earthing system test. Check the earth resistance. Now, it cannot be too large. Okay. Now, basically, it's for all earth electrodes to ensure good contact with the general mass of Earth. So the resistance, there are some standards. The resistance should be less than some number. Okay. Now, insulation resist test. This one basically is between the phases, including the bus bar, including the cable, outgoing, incoming feeders. Okay. Then you also have to do inspection and checking. Basically, it is to ensure that all joints between bus bar and all termination of cables are electrically, mechanically sound. Basically, put it simply, electrically conductive, mechanically strong. Okay, so that's the inspection. Okay, then also checking to ensure the mechanical interlocks of the incoming breakers and outgoing breakers are designed and installed correctly. So this is for interlocking system. Okay. Now, primary injection test, you need the device because you have to produce some current and inject it into the primary side of the CT. So basically to ensure that wiring connection of protection system is in order, and also check CT ratios and polarities, and also check overcurrent. OC means overcurrent, EF meaning earth fault. That means whether the settings are correct. Remember, you can use the IDMTL for overcurrent protection, right? Now where you have to determine the plug setting time multiplier, correct? Yeah. For the DTL relay, you have to set the relay current setting and also the time. Whether the settings are correct or not. Now you can check through the primary current injection test. So primary injection test is, I would say, is a very is a very effective test because it checks more than one component. Actually, it checks the whole system from CT to overcurrent relay to now the earth fault release. Okay. All right, so that's the primary current injection test. Okay. Now the insulation resistance test. I'll zoom in this a little bit. Okay, insulation resistance test now on the low voltage bus bar. Now you have to check the resistance. Now, but you need a device. Okay, insulation tester. Now usually the insulation tester apply a high voltage DC. For example, here the example says 500 volt DC. Then this voltage, is used to calculate the insulation resistance. Now you have to check, for example, brown, black. Basically, you remember you have 3 wires, not 4 wires for low voltage. You have L1, L2, L3, and the neutral. Okay. Then you can also say now the brown, black, gray, not different. So you have to check the insulation resistance between any 2 phases. Okay, that's why you have the brown, black, black, gray, gray, brown, right? So that's the different combination of phases. So you have to check the resistance between phases, and also now between phase and neutral. For example, here now you also have to check between the neutral, this resistance, how much is it? So you have different combination of brown, blue. Blue is the neutral, black, blue, and the gray, blue, right? And also between phase and the earth. Remember, there is another wire here. I should draw. Should be a now the earth. Now is a different color. Okay, so but usually we use this one, PE, physical earth. Okay, so you also have to check the now impedance between the phase and the earth. Okay, so it means, for example, between here and here. Okay, so that's the insulation resistance test. Basically, what you need actually is a pretty simple device. Is the insulation tester. Okay, you just need an insulation tester to do this. Okay, but when you do this, right, before you do this, you have to remove all the fuses first, because the fuse, if the fuses are there, your resistance will be smaller. Okay, so you have to remove all the fuses. Now disconnect the fuses, all fuses to indicator lights, to energy meter, and some other connected load. You have, and also some other connected load and the sub mains. You have to disconnect them. Then you can really now measure the impedance or resistance. Okay, so these are the something like a preparation for the insulation resistance test. All right. Okay. So we stop here for a while. We take a break, okay, then come back at 10 past 3. Okay, class. 10 past 3, we continue with this part. Okay, now let's take a break. It's 10 minutes. Yeah, 10-minute break. Okay, I'll stop the recording for now. Right.